Welcome to the second lecture of this week, and let's recall that last time we began with chapter 1 for the analysis part, and we learned what is meant by this least upper bound property of R. So we first defined what's meant by the upper bound of a subset of R, we learned what is meant by a least upper bound, and then we stated this least upper bound property of the set of real numbers. Let me recall what it said. It said that if you have a subset of R which is non-empty and it is bounded above, so S possesses an upper bound, then in fact the least upper bound of this set, the supremum of S, exists. We have a similar property with the greatest lower bound. You will see this in the homework exercises, so I have assigned this as a problem, and we will not need to assume this, but rather using the least upper bound property, you can derive this greatest lower bound property of R. Okay, so this property says that if you have a subset of R which is non-empty and is bounded below, then the greatest lower bound of this set, the infimum of S, exists. Okay, so we just assume the least upper bound property of R, and then we will deduce that R also has this property. Okay, from now on we are allowed to then use both of these properties for the set of real numbers. Okay, so what are we going to do today? Well, essentially we will finish chapter 1, and what we will begin with is an application of this least upper bound property to deduce something known as the Archimedean Principle or Archimedean Property. This will be used now and then again. So let's see what this property says. So it says the following: Archimedean Property. It says that if you have a positive real number and a real number y, okay, so you have a positive real number x and you have been given any real number y, then there exists a natural number such that n times this positive x is bigger than y. Okay, so x is positive, so if we imagine that you have something to the right of 0 on the number line, and y can be anywhere, so it might be negative, it might be positive, it might be 0. And what this is telling you is that if you look at multiples of x, x, 2x, 3x and so on, so sort of your tiling, then eventually you will exceed any y that has been given to us. Of course, if y is negative, already at the first step when you take 1 times x, you are bigger than this negative number because x is positive. Okay, but the real content is that, well, no matter what y was, it could even be positive, then if you keep tiling, of course you will eventually surpass this y. Okay, so intuitively this is a very obvious statement, but we are not allowed to rely on this intuitive picture. So let's prove this, and we will prove this using the least upper bound property of R. Okay, so let us suppose that we have been given a positive x and a real number y, and suppose that this statement does not hold. So suppose it is not the case that there exists an n such that nx is bigger than y. So this symbol is sometimes used for negation, and it is to be read as it is not the case that, and then whatever follows. Okay, so let's suppose that this does not hold. So in other words, it is not the case that there exists an n natural number such that nx is bigger than y. What does that mean? That means that no matter which natural number you take, this does not hold. That is, nx is not bigger than y. In other words, nx is less than or equal to y. Okay, so the negation of this statement is that for every n you take, nx is less than or equal to y. So now if I look at this set S, which is the set of all these nx's where n belongs to n, then this previous sentence is telling us that y is an upper bound for that, right? Because no matter which element you take from this set, it's of the form nx, but for all nx's, this is less than or equal to y. So y is an upper bound. Moreover, this set is not empty because, for example, if I take 1 times x, that belongs to this set, right? So it's not empty. And we also know it is bounded above. So by the least upper bound property, we have a least upper bound for this S. So let's call it U star. So U star, which is supremum of S, exists. So now let's take any n and let's look at the number nx plus x. Well, that's n plus 1x, and since n was a natural number, its successor n plus 1 is also a natural number. So this is a natural number times x, so it belongs to S, and U star is the least upper bound, in particular an upper bound, so it's certainly less than or equal to this upper bound U star. So if I rearrange this, if I take this x to the other side, then what we have got is that no matter which n I have, nx is less than or equal to U star minus x. Any element of the set is of the form nx, and we know that for all nx, you have that this is less than or equal to U star minus x. That means that U star minus x is an upper bound of this set. But U star minus x is strictly less than U star, and U star was supposed to be the least upper bound. So we have a contradiction. So this contradiction shows that our original assumption was not true. So there exists a natural number n such that nx is bigger than y. So this was something which was intuitively obvious, but we have now proved it using this least upper bound property of R. So we will sometimes need to use this Archimedean property. Okay, so let us consider an example, and the point of this example is that we will consolidate our knowledge by going through some of the definitions again applied to these particular instances. And besides this, we will also along the way in some of the examples need to use the Archimedean property. Okay, so let's first look at these three sets A, B and C. A is the set comprising just the three numbers 1, 2 and 9. So on the number line I have depicted them as these three orange points. The set B is the set of all natural numbers, so the set containing 1, 2, 3 and so on. So these orange points. And the set C, it's the set containing all the elements 1 by n, where n is any natural number. So when n is equal to 1, you get this element 1. When n is equal to 2, you get half. Then when n is equal to 3, you get 1/3. When n is equal to 4, you get 1/4 and so on. And they seem to become closer and closer to 0. Okay, so for these three sets, we will try to fill in this table where we want to answer the question, is the set bounded above, is the set bounded below, is the set bounded, does the supremum of the set exist, and if so, what is it? Does the infimum of the set exist? If so, what it is? Does the maximum of the set exist, and if so, what it is? And what's the minimum of the set if it exists? Okay, for these three sets. So let's start with the set A. Now this set is bounded above. In fact, any number u which is bigger than or equal to 9 serves as an upper bound. We had seen that last time. So the set is certainly bounded above because the set of upper bounds is not empty. Is the set bounded below? The answer is again yes, because any L which is less than or equal to 1 serves as a lower bound. So this set is also bounded below. Is the set bounded? And the answer is again yes, because it is both bounded above as well as bounded below. Does the supremum of the set exist? Yes, we had seen that last time 9 is the least upper bound. Similarly, does the infimum of the set exist? That's also true. It is equal to 1. We had seen that last time. And we also see that the supremum of the set, which is 9, belongs to the set again. And so the maximum of the set exists and it is equal to 9. Similarly, the infimum of the set, which is 1, again belongs to the set. So the minimum of the set also exists and it is equal to 1. So now let's look at the set of all natural numbers. And we claim that the set is not bounded above. And that is intuitively clear because if u wanted to be an upper bound, then it can't really, because there will be natural numbers which surpass u. So we can actually now prove that using the Archimedean property. So let us suppose that this B is bounded above and let u be an upper bound. Okay, so this u is some real number. Let's take that as y in our Archimedean property, and let's take x as equal to 1 in our Archimedean property. So then the Archimedean property guarantees that there exists a natural number n such that n times x is bigger than y. In other words, n times 1 is bigger than y, which was u. So n times 1 is bigger than u. So in other words, n is bigger than u. So there exists a natural number which will be bigger than this claimed upper bound, which is a contradiction because the upper bound was supposed to be bigger than all the elements of n. Okay, so this contradiction shows that an upper bound for this set B cannot exist, and so this set is not bounded above. Now, is the set bounded below? And the answer is yes, because any natural number is bigger than or equal to 1. So it's certainly bounded below. Is it bounded? And the answer is no, because although it's bounded below, it is not bounded above. Okay, so the set of natural numbers is not bounded. Does the supremum of the set exist? And the answer is no, because the set does not have an upper bound at all, much less a least upper bound, and so the supremum of the set does not exist. Does the infimum of the set exist? And the answer is yes, and let's prove that in fact the infimum is equal to 1. We already know that 1 is a lower bound because every natural number is bigger than or equal to 1. Okay. Now, if you have any lower bound, let's call it L, then this L, being a lower bound, should be less than or equal to all the members of N. So in particular, it will be less than or equal to 1. So any lower bound is less than or equal to 1. Okay, but 1 itself was a lower bound, and so 1 is the greatest lower bound, because for any lower bound, first of all, 1 is a lower bound, and for any lower bound L, we have just proved that L is less than or equal to 1. So the infimum does exist and it is equal to 1. The maximum doesn't exist because the supremum doesn't exist, and the minimum exists because the infimum, which is equal to 1, is in fact an element of this set. It's a natural number, so the minimum is equal to 1. Now let's look at the final set, which is the set C, which comprises the reciprocals of the natural numbers. So the set containing 1, half, 1/3, 1/4, and so on. Now, is the set bounded above? And the answer is yes, because 1 serves as an upper bound. For any natural number n, you have that n is bigger than or equal to 1. In other words, 1 by n is less than or equal to 1. So 1 is an upper bound. So the set is bounded above. Is it bounded below? Yes, because 0 serves as a lower bound. You see that for any natural number n, that's a positive number, so 1 by n is also a positive number. So 1 by n is strictly bigger than 0 for every natural number n. So 0 serves as a lower bound, so this set is bounded below. Is it bounded? And the answer is yes, because it is both bounded above as well as it's bounded below. Now the supremum of the set, does it exist? And the answer is yes, and we claim that 1 is the supremum. Now we already know that 1 is an upper bound. Okay. Now we'll show that it's the least upper bound. So let us suppose that u is any other upper bound. Okay. So then this u must be bigger than all the elements of the set. In particular, it should be bigger than or equal to 1. Right? So in other words, 1 is less than or equal to u. But we had already seen that 1 is an upper bound, and now we have discovered that any other upper bound u is in fact bigger than or equal to 1. So this 1 is the least upper bound of this S. Now, since this is a non-empty subset of R, which is bounded below, we know that the infimum of the set does exist by the greatest lower bound property of R. And let us now show that the infimum is equal to 0. Okay, so we already know that 0 is a lower bound, okay, because each element of this is positive. Okay, so it's bigger than or equal to 0, so 0 is a lower bound, that we already know. But now we'll show that it's the greatest lower bound. So for any lower bound L, we want to show that L is less than or equal to 0. So let us suppose that it's not the case that L is always less than or equal to 0. So suppose that there's a lower bound which is positive. Now intuitively we know that we will get a contradiction, because if you have a positive number, it's to the right of 0. But then, since these numbers are decreasing, eventually it will become below this L, right? Which will be a contradiction because L was supposed to be a lower bound. Okay, so that's where we are heading. So let us suppose that you have a lower bound L which is positive. Now we want to show that there is an element of the set which is actually even smaller than this L. Okay, so we want an n such that 1 by n is strictly less than L. But that's the same as saying that NL is strictly bigger than 1. And that we know is possible by the Archimedean principle. We are guaranteed that there exists such an N. Indeed, we can take this as our Y, which is the number 1, and L, which we have assumed is a positive number, we take as our X. Then by the Archimedean principle, we know that there exists a natural number N such that N times L is bigger than 1. That is, Nx is bigger than Y. So rearranging, we then know that 1 by N is strictly less than L for this particular N, and that means that this L cannot be a lower bound. So that is a contradiction, and this contradiction shows that such a positive number which is a lower bound cannot exist for this C. So any lower bound has to be less than or equal to 0. In other words, 0 is the greatest lower bound because it's a lower bound, and for any other lower bound L, you have that L is less than or equal to 0. Okay, so we have managed to show that the infimum of this set C is equal to 0. Now, the supremum of this set is 1, which does belong to the set, and so the maximum of this set exists and it is equal to 1. Does the minimum of this set exist? So the question is really the infimum of this set C, which is equal to 0, is that an element of this set C? And the answer is no, because 1 by n is never equal to 0 for any natural number n, because this is always positive. It's strictly bigger than 0, so it can't be equal to 0. So the minimum of the set does not exist. Okay, so now using the Archimedean property, we will prove the following important theorem. So this theorem says that Q is dense in R, by which we mean that if you have any two real numbers A and B, and A is strictly less than B, then there exists a rational number between A and B. So there exists a rational number R such that R is strictly bigger than A and strictly less than B. So pictorially we have the following. Here is the real line, and here are the two numbers A and B, and A is strictly less than B. So this A and B decides a patch on the real line, and then this theorem is saying that no matter which such patch you consider, there exists a rational number in this patch. So why do we summarize this result by saying that Q is dense in R? Well, we use the word dense in English. For example, we might say that pine trees are dense in these woods. Okay, so the picture that then we have in mind is that we have these woods, and no matter which patch of the woods you take, there is a pine tree there, right? So that's intuitively the picture that we have when we say that the pine trees are dense in the woods. So think of the woods as being the real line and the pine trees as being the rational numbers. So then this result is saying that no matter which patch you take on the real line, you have a rational number existing there. Okay. So we will need this theorem now and then in the exercises, and it's an important theorem. Okay, so to prove this theorem, we will use the following lemma, which says that if x is any real number, then there exists an integer m such that x is bigger than or equal to m and strictly less than m plus 1. So in other words, no matter which real number you take, there exists an integer m such that x lies between m and the next integer, which is m plus 1. Now this lemma is intuitively quite clear, because let's imagine the number line where you have a chosen positive length, and by reproducing it over and over again, we get the integers. So 0, 1, 2, 3 on the one hand, and by repeating the length on the other side, you also get the negative integers, minus 1, minus 2, minus 3, and so on. So now imagine these integer points as being milestones, and imagine this number line to be a long road. Now, if you have any real number, then that lies somewhere along this road, and of course, then that point lies between two adjacent milestones. So there exists some milestone m such that this x lies between m and m plus 1 and the next milestone. So x is bigger than or equal to m and strictly less than m plus 1. So this result is intuitively quite clear, but let us give a rigorous proof using the Archimedean principle. Okay, so we'll now prove this lemma, which says that if x is any real number, then there exists an integer m such that x is bigger than or equal to m and strictly less than m plus 1. So we have been given an x, and the task is to produce this integer m such that this happens. Now, by the Archimedean principle, we know that since 1 is a positive number and since this is some real number, there exists a natural number n1 such that n1 times 1 is strictly bigger than x. And similarly, since minus x is some real number and since 1 is a positive number, we know that there exists a natural number n2 such that n2 times 1 is strictly bigger than minus x. So if I rearrange these two, then we know that this x is strictly less than n1 and x is strictly bigger than minus n2. Okay, so we have got this, but this minus n2 is strictly less than n1. So this integer minus n2 is strictly less than this integer. And there are only finitely many integers in between these two. In fact, they are minus n2, then minus n2 plus 1, all the way up till n1 minus 1 and then n1. So if I look at all the integers which are bigger than or equal to minus n2 and less than or equal to n1, there are just finitely many, namely precisely these, minus n2 plus 1, all the way up till n1 minus 1 and then n1. Okay, and let us now consider this set, which is the set of all integers which are in between minus n2 and n1. And moreover, we also demand that the integer be less than or equal to x. So then this set is a finite set because first of all, there were only finitely many integers in between minus n2 and n1, and moreover, we are demanding something more. So this set S is a finite set, and moreover, it is not empty because we claim that k equal to minus n2 belongs to this set. Indeed, when I take k equal to minus n2, you have equality over here, so this is satisfied. And moreover, minus n2 is strictly less than n1, in particular less than or equal to n1. So this minus n2 certainly satisfies this. And moreover, minus n2 is strictly less than x, and in particular less than or equal to x. Okay, so k equal to minus n2 also satisfies this. So minus n2 certainly belongs to this set. So this set S is a finite set, and moreover it is not empty. So it's just a finite collection of integers, and there is at least one integer in there. So then we can take the largest among these integers. Okay, so the maximum of this set exists, and let's call that as m. Okay, so we claim that this m does this job. Okay, so let us first notice that this m, being the maximum of this set, certainly belongs to the set. So this m certainly satisfies this, that m is less than or equal to x. So we have got this. So we already know that this m is less than or equal to x. And now the task is also to prove that x is strictly less than m plus 1. So here is our claim. We claim that x is in fact strictly less than m plus 1. So let us suppose that this is not true. What does that mean? That means that x is bigger than or equal to m plus 1. So in other words, m plus 1 is less than or equal to x, but x we know is strictly less than n1. So we know that m plus 1 is strictly less than n1. So if you think of this k as being m plus 1, then we already know that this m plus 1 is strictly less than n1, so it's certainly less than or equal to n1. So this part is satisfied by k being m plus 1. Now let us also show that this m plus 1 is bigger than or equal to minus n2. Okay. So first of all, let's notice that this m, since it belongs to this set, is bigger than or equal to minus n2, right? So m is bigger than or equal to minus n2, and if I add 1 to both sides, then I also know that m plus 1 is bigger than or equal to minus n2 plus 1, but this is strictly bigger than minus n2. So we know that this m plus 1 satisfies that it's strictly bigger than minus n2, so bigger than or equal to, and strictly less than n1, so less than or equal to n1 as well. And we also know that this m plus 1 is less than or equal to x. So it also satisfies this. So this m plus 1 belongs to this set. Okay. But m was supposed to be the maximum of this set. So m is supposed to be bigger than or equal to each of the members of this set. And so it should be bigger than m plus 1 also, because it belongs to this set. We have just seen that. So m should be bigger than or equal to m plus 1, but that is absurd because m is actually strictly less than m plus 1. Okay, so we have arrived at a contradiction, and this contradiction shows that our assumption that x is bigger than or equal to m plus 1 cannot be true, and so we have proved our claim that x is strictly less than m plus 1. So we have got that x is also strictly less than m plus 1. Okay, so to summarize, how did we prove this lemma? Well, we were given the x, and then using the Archimedean principle, we produced these two integers n1 and n2. And then we looked at this set obtained from n1 and n2, and then we showed that it is a finite set and it is non-empty, and so it has a maximum, and that maximum was this m, and then we showed that this m has all these properties. We have just proved this lemma, which says that for any real number x, there exists an integer m such that x is bigger than or equal to m and strictly less than m plus 1. And this integer m we sometimes denote by this symbol, and it's called the greatest integer part of the real number x. So that's just some terminology and this notation. Now we had proved this lemma because using that we wanted to prove this theorem, which says that the set of rational numbers is dense in the set of real numbers. In other words, whenever you have two real numbers a and b such that a is strictly less than b, there exists a rational number r such that r is strictly bigger than a and strictly less than b. So now let us complete the job and let us prove this theorem. So to prove this theorem, we will use the Archimedean property once again. So first let's notice that since a is strictly less than b, this means that b minus a is a positive number. Meanwhile, 1 is a real number, and so by the Archimedean property we are guaranteed a natural number n such that n times this positive real number is bigger than 1. So this means that nb minus na is strictly bigger than 1, and rearranging you get that na plus 1 is strictly less than nb. Now this a is a real number, and so na is also a real number, so we can look at the greatest integer part of this real number na. So this is an integer, and to that you can add 1 and you get some integer. Let's call that as m. Now what's the property of this greatest integer part of na? Well, that's the integer such that you have that it's less than or equal to na, and na in turn is less than the greatest integer part of na plus 1. Okay, but this greatest integer part of na can be expressed in terms of this m. You see that this is equal to m minus 1, so we have this is equal to m minus 1, that's less than or equal to na, and this greatest integer part of na plus 1 is exactly what we have called m, so we get this. Okay. Now we can divide throughout by n. Recall that n is a natural number, so when we do this division the inequalities are preserved. So if we divide throughout by n, then we get that m by n minus 1 by n is less than or equal to na by n, which is a, and that in turn is less than m by n. Now this m is an integer and n is a natural number, so this m by n is a well-defined rational number. And we claim that this rational number does have this property, that it lies in between a and b. First of all, let's note that a is strictly less than m by n. So if you take this as your r, you have already got that a is strictly less than r. Okay, so we have already proved this thing. And now let us show that this r is also strictly less than b. Okay, so from over here, we know that m by n is less than or equal to a plus 1 by n. And if we do some algebra over here, then you see that this is na plus 1 by n. But na plus 1 is strictly less than nb, and if I divide both sides by n, you get that na plus 1 by n is less than nb by n, which is equal to b. So you have also got that m by n, which is our r, is also strictly less than b. Okay, so we have got this thing. Alright, so given the a and b, we first produced the n by using the Archimedean property, and then we knew this real number na, so we could take its greatest integer part, we could add 1 to it, and we got this integer m, and then we showed that m by n, this rational number, is indeed something which lies in between a and b. So that's how we proved this theorem. So now we have showed this important result that the set of rational numbers is dense in the set of real numbers. So far what we have seen is we started the lecture by recalling the least upper bound property, and then we proved the Archimedean property, and then essentially we have seen some uses of the Archimedean property. So now what I want to do is to sort of tell you about some terminology and some new notation. Now this new notation is for certain special subsets of the set of real numbers, and these special sets are called intervals. So what are intervals? So if you think of the real line as the set of the real numbers, I mean the number line as the set of real numbers, then the intervals are subsets which are basically segments. Okay, so these are sort of connected sets, and these are things that you can draw without lifting your pencil. But of course, we'll give a mathematical definition, but that's the picture that we have in mind. And these kind of sets, they keep appearing again and again. So rather than each time specifying what the set is, we simply develop some succinct notation with which we immediately know what interval we are talking about. Okay, so this is just some terminology and some new notation that we are going to learn for these intervals, which are these connected subsets or segments on the number line. The following types of sets are called intervals. Okay? So A and B are any real numbers and A is strictly less than B. Then this curved bracket A comma B curved bracket is the notation for the following set. It's the set of all x's which are strictly bigger than A and strictly less than B. Okay, so on the number line, when A is less than B, A is to the left of B, and then we are looking at all the points which are strictly between these. So x is strictly bigger than A, strictly less than B. So A and B are themselves not allowed to be in this set. So that's why I have indicated them by holes here. Okay, so only the orange bit in between these 2 points, okay, but not these 2 points, are there in this interval. So whenever I have a strict inequality, I use a curved bracket, and when I have a less than or equal to, I will use a square bracket. So in contrast to this set that we have just met, let's look at this new notation, which is square bracket A comma B square bracket. So what does this mean? It's just the symbol for the set of all x's in R such that x is bigger than or equal to A and less than or equal to B. So again, if these were my 2 points, then it's all the numbers in between A and B, all right, but also x equal to A is allowed because you have not strict inequality here, but less than or equal to. So A is allowed to be, x is allowed to be A, and similarly x is also allowed to be B because you have less than or equal to here. Rather than write these long expressions, when I write curved bracket, we immediately know there's a strict inequality there, and whenever I write a square bracket, we immediately know we mean less than or equal to. So we can also have this notation, which is curved bracket A comma B square bracket. So what's that? That means the set of all x's such that x is strictly bigger than A because you have a curved bracket and less than or equal to B because you have a square bracket. So that's if A and B were these 2 points, then this A is not allowed to be in the set because you have a strict inequality here, but B is allowed because you have less than or equal to. So all the numbers in between A and B, A excluded, so that's why there's a hole here, B included, that's why it's a filled point over here. That's this set, okay, and that we denote by this symbol. Similarly, square bracket AB is the set of all x's such that x is bigger than or equal to A and strictly less than B, and that looks like this: A included, B excluded, and everything in between included. Now this is the notation. So curved bracket A comma infinity is the notation. This infinity just means that there is no inequality at that end. Okay, so this just means the set of all x's such that x is strictly bigger than A. Okay, so this is just the notation for that. So if A were here, then we are looking at all the x's which exceed A, and A is not allowed to be in the set because we have a strict inequality here. So don't think of infinity as some number or something like that. It just is the notation to mean that other bounding inequality is not there. Alright, and similarly we can have square bracket A infinity to mean the set of all x's in R such that x is bigger than or equal to A. So now again we are looking at all the x's which are bigger than A, and A is allowed in the set also because x is allowed to be A because you have bigger than or equal to. Similarly, minus infinity B just means that the lower bounding inequality is not there. So it's the set of all x's such that x is strictly less than b. So it's all the points to the left of b, and b is excluded, so that's why there's a hole there. And similarly, minus infinity b square bracket means it's the set of all x's which are less than or equal to b. So all the points to the left of b, and b is allowed to be in the set. And sometimes minus infinity infinity just means that there are no bounding inequalities at all, so it's the whole of R. Okay, so this interval just means it's the whole of R. So what we have learned is that, well, intervals can be any of these sets, and each of these sets have this property that, you know, it's nice and connected and it's sort of a segment. And this is just succinct notation to avoid writing these, you know, cumbersome expressions, because these kind of sets keep appearing all the time, and we don't want to. We have just developed some succinct notation for that. Okay, so some intervals are going to play a more important role, and in this course in particular, we will often meet compact intervals. So these are intervals which are bounded, and also endpoints are included. So a and b are real numbers, a is strictly less than b, and then we are going to look at this interval square bracket a comma b square bracket, which is the collection of all points in between a and b with endpoints included. So such an interval is called a compact interval. Now this compact actually means a certain precise mathematical thing which this set does have, but right now for us it is just some terminology to easily refer to this kind of a set. Now in MA 203 you will discuss compact sets in general in more detail, but for now it is just a name given to this special type of an interval. Okay, so it's a bounded interval with endpoints included. And also important are these kind of intervals which we refer to as open intervals. This just means that the endpoints are not included. So the sets, a bounded set like a comma b, or a half ray from starting from a onwards, but a is not included, or a half ray in the other direction from minus infinity to b, anything less than b, and b is not included, or the whole of R. None of the endpoints are there, and you're looking at all the real numbers. So all of these are open intervals, and again this open means something precisely, but that you will learn in MA 203. Okay, so right now it's just a name for these type of intervals. We sort of collectively call them as open intervals. Okay, so one more very important thing that we will now discuss is the notion of distance in R and the absolute value. Now absolute value is something that you probably are familiar with. So for example, the absolute value of 3 is equal to 3, the absolute value of minus 3 is equal to 3, and the absolute value of 0 is equal to 0. So basically absolute value is when you forget about the sign and you just take the positive number or the non-negative number. And the reason that we are revisiting this is because we want to define the distance in R. So this is going to play a very important role in calculus, because or in analysis, because in calculus we are familiar with notions such as differentiation and integration and so on. So for example, if you revisit how you define the derivative of a function at a point, what you look at is the limit of the difference quotients. Okay, and what does this limit mean? Well, it's the value to which this difference quotients seem to settle down to. In other words, they're approaching this number. Okay, and what does approaching mean? Well, that means that in some sense they're getting closer and closer, they're settling down to that value. So in order to talk about closeness of real numbers, we need a notion of distance in R. And it turns out that this distance is succinctly expressed in terms of the absolute value. To see why, so for example, if you think of the real numbers as numbers on the number line, then the distance between 1 and 2 is 1, the distance between 1 and 3 is 3 minus 1, which is 2. And in general, if you have two numbers x and y, right, then you take the larger number and you subtract the smaller number, and that's the distance between the two. So if you have two numbers x and y, two real numbers, and if y is bigger than or equal to x, then the distance between y and x is y minus x. But if x is on the right of y, in other words, if x is bigger than or equal to y, then the distance would be x minus y. So notice that this y minus we are taking y minus x if y minus x is bigger than or equal to 0, and if y minus x is less than 0, then you are taking the minus of that. In other words, this is nothing but the absolute value of the difference between the two numbers, right? So the only role of the absolute value is that it gives us a succinct way of expressing this distance. Okay, so let's recall what is the notion of absolute value. So if you have a real number x, then the absolute value of this x, which we will denote by mod x, sometimes read, instead of saying absolute value of x, we'll simply say mod x. Mod x, or absolute value of x, is defined by x if x is bigger than or equal to 0, and minus x if x is less than 0. And as we discovered above, the distance between two real numbers x and y is then mod of x minus y. Okay. So this distance between x and y I will sometimes denote by d of x comma y. Okay. D for distance and between this pair of real numbers x and y. Okay, so we now want to prove some simple properties of the absolute value and the distance, which will be used again and again. Okay, so some of these properties are quite obvious and in some sense a bit painful to verify, but let's do it anyway, because then once and for all we have checked it and we are then ready to use it, right? So that's the idea. So the first thing I want to say is the obvious thing that for all real numbers x is less than or equal to its absolute value, and also minus x is less than or equal to its absolute value. So this is a thing that we will keep using again and again, and that's useful to know, right? So let's once and for all see the proof. Now of course we know that when we take the absolute value, you're making it sort of positive, yeah. You're forgetting about the sign, and of course it's going to be bigger than or equal to the number itself or minus of that number, right? But let's prove this. So let's consider first the case when x is bigger than or equal to 0. Okay, then mod x by definition is itself. So in fact, in the first thing we even have equality, right? So x is certainly equal to mod x, and in particular less than or equal to. And since x is bigger than or equal to 0, if I rearrange this, bring x to this side, I have minus x is less than or equal to 0, and that's less than or equal to x because x is bigger than or equal to 0, so that's why this inequality is true. But x is mod x in the case when x is bigger than or equal to 0. So we have also got that minus x is less than or equal to mod x, so the second thing is also true. So we are done in the case when x is bigger than or equal to 0. What about when x is strictly less than 0? In that case, by definition, mod x is minus x, yeah. And so again, we have equality now. In this case, minus x is equal to mod x, in particular less than or equal to, so we have already got the second thing. And if x is strictly less than 0, then you already have this thing, and moreover, if I bring this x to the other side, I have that minus x is bigger than 0, but minus x is what mod x is in this case, and so you have that x is strictly less than mod x, so you have a strict inequality over here. So in particular it's less than or equal to. So in this case also we have both of these things. So now we are ready to use this again and again. So now what I want to prove is this theorem, which is also something which will occur often. And what I want to prove in this theorem is to understand all the x's whose distance to c, okay, so this is the distance between x and c, mod of x minus c, when it is less than epsilon. What does that set look like? And I want to convince you that that is in fact an interval, and it's the set of all x's which lie in between c minus delta and c plus delta, endpoints excluded. So in other words, it's this open interval from c minus delta to c plus delta. So this is your A and this is your B. So it's a symmetrically placed set about the C. So you have the C, and then you go distance delta on the left, a distance delta on the right, and all the points in between here is exactly this set. Now from here to here, that's just the definition of this open interval. So there is no content in this equality, but this is the main thing, that this inequality is somehow equivalent to these two inequalities. So that's what we want to show. So to show that this set is the same as this set, I have to show that you have this set is included in this one, and vice versa, this set is included in the other one. So let's start with the fact that this set is included in this one. So suppose that mod x minus c is less than delta. So then in particular x minus c is less than or equal to its mod. That was because of the previous lemma. Any number is less than or equal to its mod, and this we know is less than delta. So we already get the inequality if I bring the c over to the other side, that x is less than c plus delta. Now we also know that minus of any number is less than or equal to its mod, again because of the previous lemma. So and moreover, this is less than delta. That was the assumption. And so if I rearrange this thing, I get, if I take the x to the other side and delta to this side, I get c minus delta is less than x. So putting these two together, I have indeed that x is less than c plus delta and bigger than c minus delta. In other words, it belongs to this set. So this set is included in this set. Vice versa, now let's start with this set. An element from this set, namely, let's take an x which satisfies these two inequalities. X is less than c plus delta and c bigger than c minus delta. Well, if you have from this inequality, by rearranging, if I bring this x to the other side, I get minus x plus c is less than delta. I bring delta to the other side, and this inequality says that if I bring c over to this side, x minus c is less than delta. Now I want to say that mod x minus c is less than delta. Now what's mod x minus c? If x minus c is bigger than or equal to 0, it's x minus c. And if x minus c is strictly less than 0, then it's minus of this, which is minus x plus c. But you see, if we are in this case, when x minus c is bigger, it is this number. But that number we already know is less than delta because of this thing. And if we are in this case, then the number is minus x minus c, but that also we know is less than delta. So no matter which case we are in, it's always less than delta. And so mod x minus c is less than delta, and so whenever you have an x in here, it's also in here, so also this set is included in here. So this inequality is equivalent to this one. Okay. Okay, so now I want to show another sort of mundane kind of fact, namely that when you have any two real numbers, then the absolute value of their product is the product of the absolute values. And again, this is a sort of painful verification, but let's do it once and for all so that then we have seen the proof. So if A or B is 0, then the product is certainly 0. So the left hand side is just the mod of 0, which is 0. On the other hand, if A or B is 0, one of the two mods will certainly be 0, right? And so mod A times mod B will have one factor will be 0, and so the right hand side is also 0. So we have equality. Now in the cases when none of them are 0, we have four cases: A positive, B positive, A positive, B negative, A negative, B positive, and A negative, B negative. So let's get rid of them one by one. So if A is positive, B is positive, then AB is positive. So the left hand side is then just mod of AB, which will be AB because AB is positive. But since A is positive, A is mod A, and since B is positive, B is mod B, and so this is mod A times mod B, which is the right hand side. If A is positive and B is negative, then AB is negative, so the mod of AB will be minus AB, but I can write this as A times minus B, and A is mod A because A is positive, and mod B is minus B because B is negative. So you have this is the right hand side. If A is negative and B is positive, then this is essentially the same as 3 with A and B interchanged or swapped, and so that's the same argument. If A is negative and B is negative, then AB is positive because both of them are negative, and so its mod is AB itself, but that I can write as minus A times minus B, and minus A is what mod A is because A is negative, and minus B is what mod B is because B is negative, and so this is the right hand side. So this was also a straightforward verification, but now we have this, we have proved this, and we are allowed to use this whenever we want. Now here is one more important thing, which is the triangle inequality, and this is very, very important. So you should memorize this inequality, and it says that if A and B are any two real numbers, then the absolute value of their sum is less than or equal to the sum of their absolute values. Okay, so we don't have equality here, you have less than equality, and this is a very important inequality because we will use that often to bound things above, and this will play a very important role in analysis. So let's quickly prove this. Well, if A plus B is non-negative, then the left hand side is the absolute value of A plus B, but since this is non-negative, this is A plus B. But A itself is less than or equal to mod A, and so this is less than or equal to mod A plus B, and B itself is less than or equal to mod B, so this is further less than or equal to mod A plus mod B, and we are done. If A plus B is negative, then mod A plus B is minus of A plus B, which is minus A minus B, but minus A itself is less than or equal to mod A, and minus B itself is less than or equal to mod B, so you get this inequality, and that proves this theorem. Now why is it called the triangle inequality? We'll see in a minute, but before we do that, let me tell you about an important and useful consequence of this triangle inequality, which is sometimes called the reversed triangle inequality. So this you will do as one of the homework problems. I assigned that, and so you will see how to prove this. But you will use the triangle inequality to deduce this one. And what does this reversed triangle inequality say? It says that if A and B are any two real numbers, then the absolute value of the difference between the absolute values is less than or equal to the absolute value of the difference of the two numbers. Why reversed? Well, here the mod A and mod B are appearing on the bigger than or equal to side, on the bigger side, whereas here they are appearing on the smaller side, so that's why it's somehow reversed. But I mean, so you will see a proof of this, and you should also memorize this inequality because we will have to use that over and over again, and over the weeks we will get more and more proficient in using these two inequalities. Right now, of course, it might be a bit of a mystery as to how exactly we use this, but we will see that in the chapters on limits and convergent sequences, we will often have to estimate things, and also in the chapter on continuity, and there these two inequalities are indispensable. So it's very important that we memorize them, and also we will see how to use them over the weeks. So we have proved this triangle inequality, and let me point out a very simple corollary of this. If x, y and z are three real numbers, then the distance between x and z, recall that that's just the absolute value of the difference of these two numbers, is less than or equal to the distance between x and y plus the distance between y and z. Well, let's quickly prove this. The distance between x and z by definition is the mod of x minus z. Now I want to somehow get a y. I don't see a y, so let's artificially create it by adding and subtracting y. So I'll have x minus y plus y, so y minus z. Okay. So this minus y plus y is really 0, so I've not done anything to this one. So nothing has happened. But now I think of this as a real number a, this is a real number b, so this is of course less than or equal to the mod of the first real number x minus y, mod of the second real number, which is y minus z, by the triangle inequality. And this is nothing but, by definition, the distance between x and y, and this is nothing but the distance between y and z. So we have got our inequality. And this inequality reminds us of the usual triangle inequality in the plane in Euclidean geometry. So you may or may not have seen this, But it turns out that in Euclidean geometry of the plane, if you have any triangle XYZ, then right, with the vertices X, Y, Z, then the distance between X and Z, so this side length is less than or equal to the distance between X and Y, this side length, plus the distance between Y and Z, which is this side length. In other words, in any triangle, any side length is less than or equal to the sum of the other two sides. Okay. So this is a bit like that, and that's why people call this inequality the triangle inequality. Now, this distance function that we have, which takes two real numbers and tells you their distance. So distance between x and y is the mod of x minus y. That function has these easily verifiable properties. I just list them because these will play a role in MA 203. So let's look at these as some curious properties right now. So I label these three properties as D1, D2, D3. Okay, so these are nothing but it's a list of properties which is satisfied by this distance function. So for any two real numbers, the distance between x and y is of course the mod of x minus y, which is of course always greater than or equal to 0. Moreover, if the distance between two real numbers is equal to 0, so if mod x minus y is equal to 0, well, the only number whose mod is 0 is 0. So x minus y is equal to 0, which means x is equal to y. Okay, so it has this first property. That's sometimes called positive definiteness, but we don't have to worry about that. The second property is a symmetry property. The distance between x and y is the same as the distance between y and x. And that's also very obvious, because what's the distance between x and y? That's mod of x minus y. But that you can write as minus 1 times y minus x. And the mod of AB is mod A times mod B, so it's mod of minus 1, which is 1, times mod of y minus x, which is the distance between y and x. So it's clear that this is true. And this third thing is the triangle inequality, which we have just proved. Okay, all right. So you will see that in MA 203 we want to extend calculus, and then we'll start with this distance function, and we will see how to generalize it to also do calculus in more exotic settings, like in finite dimensional vector spaces and things like that. Okay. All right. So I just want to make a little remark about the construction of R. So far we have relied on an intuitive picture of R as being the points on the number line, or things having decimal expansions or something like that, and then to prove theorems and so on, we stated these precise properties. So we think of R mathematically as an undefined set for now, which has these properties: the field axioms, the order relation properties, and then the least upper bound property. Okay, and then we proved lots of theorems starting from these properties. But the question is, well, what is R really as a mathematical set? Well, for the students of MA 103, we will discuss this in the length term, and we will give a construction of R by using the rational number system. So we'll see precisely what this R is, and not only that, we'll also show the properties that we have been using. Okay. But for others, we in first courses in calculus, we often start with an intuitive understanding and state precisely the properties of R that we are allowed to use, and that's what we have done. Okay, but the construction of R will come later on.